Okay, hello everybody. Welcome to Engineering 210 review session. Let me move my mic a bit closer. Engineering 210 review session number 6. Today we will be basically only talking about capacitors because that is what this quiz will be on. So capacitors. What is a capacitor? Hopefully you all learned this in like physics, but a capacitor is at the most simple level, it's like you can think of it as like two metal plates separated by a distance with wires going in and out of them. And what happens is if I put a current source or like if I put current into the capacitor, then it will send current in here and it'll like charge up this plate to be positive. And the more current that I send into the plate, the higher the voltage difference will be between the two plates. So as current goes in, we charge up with a voltage. And that's cool. Um, I'll leave that drawn actually. In a circuit, so that's with the current source. However, most of the time we're dealing with like voltage sources. With a voltage source, what will happen is this capacitor over time will charge up. So let's say this is 2 volts. Then eventually, so what'll happen is if the capacitor, there will be no inductors on this quiz, correct? Um, when you connect a voltage source to it, let's say this started completely uncharged, what would happen is current would flow into the capacitor until enough charge built on it that we had a 2-volt difference across here in the same way. So you can think of it like, okay, the positive charges are flowing out of the voltage source onto the capacitor. Of course, in reality, there is no positive charges, it's electrons, but we live with the decisions of people who guessed wrong like 100 years ago. Um, so the general idea is for DC circuits, so circuits where the voltages like don't change and stuff like that, the capacitors will end up charging to like whatever voltage they would be if there was an open circuit there. And this will make a lot more sense when I start doing practice problems. But like one more example, if we have a voltage source and we have this is actually a much better example. So we have like a resistor and a resistor, and then across one of the resistors, we put a capacitor, and we want to say, I'll make up some values here. Let's say this is 6 volts, this is 2 ohms, and this is 1 ohm, right? And we want to say, okay, what will the voltage on this capacitor be as time goes to infinity? So that means after the capacitor is fully charged, what is the voltage of the capacitor? So let's see. As we said, the capacitor will charge until it's like what its charge would be at an open circuit. Um, And so for this circuit, if we think of this as an open circuit, so that means we can essentially pretend it does not exist, right? Then this circuit is very straightforward. You would just get like, okay, we have 6 volts here, and then by voltage division, we'd have 4 volts here, and we'd have 0 volts here. So that means this voltage across this capacitor would end up charging to like 2 volts. And now the way that the questions that will be given on the quiz will be talking about, okay, what is the function of the charge on the capacitor over time? And the function given is, give me a sec to find it, that the voltage of a capacitor at a given time is equal to the voltage of the capacitor at infinite time, so like the steady state voltage of the capacitor, plus the difference between the initial voltage of the capacitor and the steady state voltage of the capacitor, times e to the minus t over tau. What this is saying is that if I have a capacitor that starts at like V1 and then it goes to V2, so at V1 would be like the time equals 0. Let's say, I don't know, I'll say this is 1 volt example, and it goes to like, I don't know, 11 volts. And then what this function would look like is we'd have a graph, and it would look like, okay, we start at 1 volt and we go up to 11 volts, and it's going to approach this 11 volts like this, where this tau equals R times C. The unit for capacitors is capacitance. Uh, capacitance, and that is units of farads or farad. I don't know how you say that. Farad, something like that. F. And this is called the time constant. And this is just kind of an easy way to think about how it changes. And the time constant as like a heuristic, the time constant is like the time it takes for the voltage to change by like, I think it's like 1 over E percent. Yeah, that makes sense. What's 1 over E? It's like 1 over 2.7. It's like 1 divided by 2.7. It's like 37%, I think. That feels right to me. Um, so like if 37% is like here, then this would be 1 times tau. Yeah. Um, I could be I could be misremembering what that means, but I think that's right. Um, one key thing about this equation is that you should always get a graph that starts at your initial voltage and ends at your final voltage. I know that sounds obvious, but a lot of people don't do that. So once you get your equation, you should fact check yourself, plug in 0, plug in infinity, see what you get, make sure your numbers make sense. Oh, and one other important thing that they say is that the time is greater than or equal to 0 seconds. So, and you also have to like put units on it. That's kind of a brief overview. Um, and then, oh, and finding the VC of 0 and the VC of infinity, what you do is you look at, but usually these questions will have like some kind of switch where it'll have like an arrow on it. And let's say it's like, let's say our circuit looks something like this. We have some capacitance, some resistance, and some voltage. So here, and it would say like, okay, at t equals 0, the switch moves from position 1 to position 2. Um, Here, VC of 0, we'd think about, okay, what's the voltage before anything has changed? So if we only had this half of the circuit, then it would charge up like I said here. Um, and it would just go to whatever V is. And then when for VC of infinity, it's like, okay, now it has gone the other way. So once it's moved, I'll draw it in blue. Once the switch has moved, we're over here. So I'll say VC, I'll call this V1 equals V1. And then VC of infinity, okay, well now there's like an open, this switch has moved, so this part of the circuit is no longer connected, and we only have this. So what we have here is we have a charged capacitor, and it is sending current through a resistor. And that resistor will dissipate the current. And since there's no external voltage sources in the circuit, VC of infinity will eventually go to 0. So then we'd plug all these into our equation and get our fun equation. Um, and then, oh, one more thing. If we have like a capacitor and it's connected to like a bunch of resistors, like something like that, and we're trying to find the tau. Can someone can you mute yourself if you don't have a question? Um if we are trying to find the RC and we have like a C, and this is like R1, R2, R3, then this R would be the like equivalent resistance of these three resistors. In this case, it would be like R2 in parallel with R3 plus R1. Hopefully you can see why, like these two are in parallel and then they'd be in series with that. Yeah. Um, so yeah, there's a lot I could say. I'm just going to start doing practice problems because it'll make the most sense. Um, okay, so, and also hopefully this stuff isn't too new to you. I, again, recommend going to class. Uh, Here we are. We got a switch, and at t equals 0 seconds, the switch is opening, right? Twelve ohms, 0.167 farads. Uh, if you take more electrical engineering classes, you will learn that that's an absurdly high number for a capacitance value. But for the sake of math, they give you nice numbers. Um, and it's saying find expression for a V of 4 ohm resistor after switch is opened. So when you see a question like this, you say, okay, we have to find stuff out about the 4 ohm resistor and specifically the voltage. However, we know that the voltage of things in parallel is the same. And this resistor is in parallel with the capacitor. So what we can say immediately is that V 4 ohms of T is equal to VC of T because they're connected on both ends. So they have to have the same voltage. So really what this question is asking is, okay, what is VC of T? And to do that, we have to find the initial voltage and the final voltage. Um, so let's think. So for the initial voltage, we can redraw the circuit with the switch. Basically, you think about it in two scenarios. We have the switch closed and the switch open. And with the switch closed, we have a circuit that looks like this. I think this is how it's recommended to be done. You know, you draw your circuit 1 and your circuit 2 with both states to find your two things. So this is T is less than 0. And we want to find the voltage across the capacitor at this time. So again, you treat the capacitor like it is an open circuit when you are solving circuits, because you can assume that the capacitor has fully charged up and it is no longer letting current through. And so what we see here is, okay, we're trying to find that voltage. So we have to find the voltage on top and the voltage on bottom. And let's say this is ground. I look at this and there's kind of a bunch of ways to do it. I guess the most straightforward way is just do like a node here. I'll call it V1. So we get V1 minus 24 over 6 plus V1 over 4 plus V1 over 12. Again, we ignore the capacitor because it's an open circuit in this scenario. And then we solve this, and what do you get? You get like 8 volts. Just trust me on that. I don't want to do the math. You could also do it like you can combine these two in parallel and then do a voltage divider with the two. You can do it any way you want, but you'll get 8 volts. And so we can then say VC of 0 equals 8 volts. Oh, I guess I should, before I keep going, I should talk a bit more about like capacitors like in theory. So a capacitor, the voltage across it mathematically is, or no, wait, which way is it? Forget, one of them is the inductor equation, one of them is a capacitor equation. Capacitor voltage equation. Capacitor current equation. Yeah. So the current through a capacitor is equal to the capacitance times dV dt. And what this tells you is that I of t. What this tells you is that the voltage through a capacitor is like differentiable. And that means that the voltage through a capacitor cannot change instantly. That's like kind of complicated, but basically the other way to think about this is that like this is like all math and it's useful if you do certain things, but you can also think of like if the voltage is the integral of the current over time, which makes a bit of sense because it's like you're adding up all the current that goes into the plate. Um, but basically voltage cannot change instantly. Yeah. And that's the point of this equation we have here. And I'll copy this over to the next page. And then like the simplified version of this equation, which I think you learned first, is basically just when VC of zero or when VC of infinity equals zero, it's VC of t equals VC of zero e to the negative t over tau for time is greater than or equal to zero. Yeah, back to the question. So we're here, we found VC of zero. And in this case, for the second part, so after the switch closes, or after the switch opens, because we have it, going like that. After the switch opens, we get that this part of the circuit, like there's an open circuit here, right? So we can completely ignore all of this. So now we just have, so for t is greater than or equal to zero, we get 4 ohms, the capacitor, and 12 ohms. This is 0.167 farads. All right. And as you can see here, there's no voltage source on it. So we can instantly say that like VC of infinity equals zero because the capacitor has some charge, right? And over time, it will all flow out through these resistors, and the resistors will dissipate that current like as heat. It'll dissipate all the power, and then it'll go to zero. Okay, the other thing we have to do for this t is greater than or equal to zero is find um the time constant because this is the part where the capacitor will be discharging. So the time constant tau is equal to R times C. In this case, R is going to be these two resistors in parallel because you got to combine all the resistors into one resistor. So let's see, we got 4 times 12 over 4 plus 12, and that's going to be 48 over 16, which is 3. So we get tau equals 3 times 0.167. 0.167 is like 1/6, so this is 1/2. And then, moving on, we now have all the information necessary to write that equation. So we can say VC of, or I guess if we want to be technical about the question, V of 4 ohms of T equals VC of T equals, and then we're going to fill in that equation. So it was, you can think of it as either of these two equations. In this case, since we have VC of infinity equaling zero, we can just use this equation, right? So here we got VC of zero. I'll write it out. So VC of zero e to the negative t over tau, which in this case would be 8 volts. So 8 e to the negative t over 1/2, which is then 8 e to the negative 2t. And then make sure you write the unit, and for t is greater than or equal to 0 seconds. Very important. Because if you don't write those, then you're not actually saying anything. Because, I don't know, you got to be specific like that. And that would be how you solve that question. Moving on, I will do another question. Let's see. There was like one evil question at one point. That might have not been this year. That might have been, I don't know. I don't remember when that was. I don't think it was last year. So it wouldn't be on this quiz. Yeah. Okay, this one is a good question too. I will do this now. So we got another 24-volt source. I don't know why they're both 24, but they are. Okay. So in this question, we have a switch, two voltage sources, and the capacitor. And again, what you always want to do, first, see what it's asking you. In this question, it says, find an expression for the current flow through the 4 kilo ohm resistor. So that's interesting. So, and after the switch has moved from position 1 to position 2. And the 4 kilo ohm resistor is this one, so I'll write that down. Find equation for current flow through 4K after T or for T is greater than or equal to 0. Um, so let's look at that first before we do anything. So for T is greater than or equal to 0, right? The switch is going to be in this position. And then we have the circuit like this, right? And we want to look at the current flow through this 4 kilo ohm resistor. And what that'll be is depending on the voltage of this, if this is higher or lower than the 30 volts, we'll either have like a voltage like that or a voltage like that. But generally what it'll be is it'll be the difference between the voltage here and here divided by 4 kilo ohms. So it'll be like 30 volts minus VC of T over um over 4K. Hopefully that makes sense. This question doesn't actually like specify which direction we're looking at. So I guess we'll end up doing whatever direction is positive. So this is like our goal. But generally, capacitor questions, you want to write uh you want to find a way to write the target value in terms of VC of t. And then we find VC of t the same way we have done it before. So again, like always, you start with for t is less than 0. We assume that the switch has been in this position for a very long time and has fully charged up to whatever like the steady state voltage would be for it. So hopefully you can all see that when the switch is in that left position, the circuit simply looks like this. You have 0.5 millifarads, although the value actually doesn't really matter there. 3K, 5K, and 24. And here, the voltage across this capacitor is just going to be the voltage from here to here. And that you can very quickly figure out by just like a voltage divider. Again, remember this is an open circuit, so we are only thinking about this half of the circuit when we're finding the voltage. Here we find the voltage across the 5 kilo ohm resistor. So the voltage across the capacitor at 0 volt at time 0 equals the voltage across that 5K, which is going to be 24 times 5 over 5 plus 3 by voltage division. So that's 5/8 of 24, which is like 24 divided by 8 is 3. 3 times 5 is 15. Look at that. You can do math in your head too. So VC of 0 equals 15. Cool. We did that. Now we say, okay, time is greater than or equal to 0 once the switch has closed, or once the switch has moved. Now we have a circuit that looks like this. And what we know is that this starts out at 15 volts. So cool. So what that tells us though is that, and 4K. So we look at this and we say, okay, what will this end up charging up to? This capacitor will end up charging up simply up to 30 volts at time equals infinity. If you think about it, right, this resistor will make it charge up slower. Um, this resistor will make it charge up slower, but eventually, like, it'll get there. If there's no current, then the resistor basically doesn't exist, and the voltages would just end up being the same. There's a question, when should you use voltage division? You use voltage division whenever it's easy to. There's not really a specific time. It's just like here you got like it's the path is just two resistors. You got one resistor and another, and they're in series, right? So the voltage between them, it's very easy to do as like a fraction. If you're not comfortable with it, you don't have to use it. You can always do like call this V1, V1 minus 24 over 3K plus V1 minus 0 over 5K equals 0 and solve for V1. But voltage division, it's like nice and easy. So here, again, we can say just because of this source and because there's like no other path or anything, that doesn't exist. we can just say that V of infinity is equal to 30 volts. And then we want to find the time constant. One thing I didn't mention about finding the time constant is that you will neutralize sources like the same way you did for I'll write this down like over here, I guess. When finding the taus are neutralize sources like you did for Thevenin equivalents. So that basically means this voltage source, we imagine it as shorted, and so it doesn't matter. But basically then, right, tau in this case is just going to be that 0.5 millifarad, so 0.5 M times 4K. If you haven't learned this by now, you know, milli is just like 10 to the negative 3, and kilo, or kilo is 10 to the 3. And so M times K is 1. So those cancel. Will V infinity always be the source? I'll answer that in a sec. So here, like these will cancel, and then you just have 0.5 times 4, so that's 2. Very cool. And then we plug all of these values into that cool equation at the end. VC of t, I got a text message, ignore that. VC of t equals, what was it? Memorize this. This is like the only equation you have to memorize. VC of infinity equals VC, so VC of infinity plus VC of 0 minus VC of infinity e to the negative t over tau. And this would be 30 plus 8 minus 30. No, it was 15 here. Whoops, that was the wrong question. 15 minus 30 e to the negative t over 2, which we can then simplify a little bit and write as 30 minus 15 e to the negative 0.5 t. Volts for t is greater than or equal to 0. And then we want to say, okay, what is the current through that 4 kilo ohm thing? And as we found that the voltage on this capacitor is going to be lower than the voltage source, that means that current will be flowing this way, right? Because the voltage source is going to charge it up. So then I actually, when I guessed, this was correct. That's in the right order. So if we want to say then the current through that 4 kilo ohm 4 time t is going to be 30 minus this equation we just had. 30 minus 30 minus, or 30, I'll put in parentheses. 30 minus 15 e to the negative 0.5 t over 4k. And the positives or the minuses will cancel and the 30 goes away, and we get like we get 15 over 4k e to the negative 0.5 t amps for t is greater than or equal to 0. Let me make sure I got that right. I don't think, oh wait, no. Oh, okay, yeah. If you actually like divide it, you get a number. Or wait, did I do this wrong? I might have done this wrong. Hold up. Oh, no. That's right. Yeah. The other way you can think about it, actually, no, just do it that way. You can also do it with like the or I equals, I can't write anything. I equals C dV dt. And then you can like differentiate it. And that works. And that always works. Yeah. For your question as to like, will the VC of infinity always be the voltage source? Like not necessarily. Like say we had a circuit that looked like um what's a good example? Yeah, say the circuit looked like this, right? We had like a 2K here. Then for the T equals infinity circuit, we'd have something that looks exactly like that first circuit. So it would be like the capacitor, the resistor, that, that, that. And here we'd have the 4K and the 2K. And then remember, you treat this as if it's an open circuit. So we just want to find the voltage here and here, basically pretending this part doesn't exist for now. And again, by voltage division, this is like 1/3 of the total resistance. So it's 1/3 of the input voltage. We get like 10 volts here and zero. Yeah, 10 volts there. We like always like say that that would be 0 volts. So then here, like VC of infinity would be 10 volts instead of zero or instead of 30. Yeah. And then in that case, like when you write this equation, it would do what you want. One quick thing about this equation here, you can think of this equation, if you want to think about how to graph it, right? So if we're thinking about graphing it, this is our time axis, and there's 2 points of interest. We got like 15 volts and we got 30 volts. We know that at time equals 0, we're at 15 volts, and we want to end up going to 30 volts. So even before you've written this equation at all, if you have this number and if you have this number and you have this number, you can know what you want your equation to look like. It'll look something like that, approaching that, and the like slope or the rate of that is determined by that tau equals RC. And then what you can do is you can fact check and say, okay, is that what my equation looks like? And if you look here, it is. So we have the 30 volts, so that if you think of this like an exponential function, right? An exponential function is like just e to the x is like that or something. So if we look at this, we have a negative exponential function. So that would be like, that. But then, oh, it's a negative exponential, but then it also has a negative term there. So it's like that, right? And then it's plus 30. So we take like this and then move it up here. And you end up like that's the correct function. Wow. So always like fact check your answers. Make sure your equation makes sense. You can also think of this as like 30 volts is like the real thing, and then this is like some error that like decays over time. I don't know. Think about it how you want, but you should understand that the equation like should model what you expect. Yeah. More practice problems, infinite practice problems. Let's see. Which of these looks interesting? Uh, yeah, sure, I'll do this. Um, Wrong button. Okay. This one has a current source. How interesting. Wow. Uh, if you can hear my roommate shouting, I think they're like playing PUBG Mobile or something. That's not a resistor, that's just a squiggly wire. Um, and this is going like t equals 0 seconds. Yeah. Okay, 8 ohms, 1/18th of a farad. 4 ohms, 24 ohms. Oh no, 24 volts, my bad. 24 ohms and 4 amps. And this question is asking, okay, this question's chill. It's just find VCT for t is greater than or equal to 0. And again, you do it the exact same way I have said to do it the whole time. You start with the circuit before the time changed, and then or before the switch changed, and then you do the circuit after the switch changed. I realize I say like I said the whole time, but like I didn't really ever explain that formally, but that's what you do. So t is less than 0. We got the circuit for like this is position 1, this is position 2. As you can see, the arrow says it's moving upwards. So we got this. Okay, and we got that. And we want to find VC of 0. Wow. And VC of 0 in this case will it kind of looks a bit more complicated than you've seen before, but again, just remember that the capacitor is an open circuit. So we can just like say, okay, what is the voltage between this point and this point if this part of the circuit does not exist? So that's, we only have this part, right? And what this is, again, is like just voltage division. If you wanted to, you could redraw the circuit as like, um, let's see, it would be like this and then this, where it's connected like that, right? Hopefully you can see that this has all the same connections. It's just you kind of move things around a bit, right? But that's the same circuit. So what that tells us though is we can say that that will equal that input 24 volts times 8 over 8 plus 4. So 2/3 of 24, right? Because 8 over 12. And so that would give us 16 volts. Now for t is greater than or equal to 0, that switch has moved. And we got a little arrow, and we got the resistor. And now this middle branch is gone, right? Because when the switch goes here, then this doesn't matter anymore. And so now we just go all the way over there, straight to the capacitor. And we go to that 8 ohm, 1/18th farad, 24 ohm, 4 amp. And we want to find, okay, what is this? What is this voltage? And to do that, you can either do node voltage again. I'll like write so the node equation for like let's say VC of infinity, sure, equals I'll just call it V1 for the sake of writing the equation, right? The V1 equation would be okay, think about it. We got a current going in, so -4 plus V1 over 24 plus V1 over 8 equals 0, and you'd solve that. Or you could think, okay, always remember, like this doesn't matter when we're finding this. We just want to find the voltage here. However, the voltage for this is like the same as the voltage here. And then you can look at these two in parallel. So the resistor equivalent would be like 24 times 8 over 24 plus 8. I realize this math is actually not as easy as I thought it would be because I don't know what 24 times 8 is off the top of my head. Actually, wait, it's like 24. No, I don't know what 24 times wait, no, it'd be 96 times 2, which is 192 over 32, which is 6 ohms. And then so like then the equivalent circuit would be like 6 ohms in the capacitor. And hopefully you can see that this, V equals IR, just straight current through the resistor. The voltage across the resistor would be the same as the voltage across the capacitor, would be 24 volts. Right. Yeah. And then once we have that, we write the equation, which is the same equation we've had, which is VC of infinity. So this is like the final voltage plus the difference between the initial voltage and the final voltage times our function that decays down to 0. Yeah, so like I said, you can think of it as like this is the final number, and then this is like the error, and then this says that like error go to 0. Where it's not really like an error, that's just a word I'm using, but it's like this is the difference between the initial and the final, and then this says, okay, the difference between the initial and final will go to 0 as we pass through time. And this is supposed to be a minus sign. So then we plug it all in, we get VC of infinity we found earlier, right here. That equals VC of infinity. Whoops, should have labeled that. So that's 24 plus 16 minus 24 e to the negative t over, and oh no, I forgot to do the tau. But basically, this circuit that's simplified works just fine. So tau equals RC. Remember, I said we neutralize the sources the same way we did for Thevenin stuff. And that means this becomes an open circuit so that this is the only part of the circuit that matters anymore. And so it's very simply that 6 times 1 over 18th, if you look at what we had before, and that is 1/3. Yeah. So t minus t over 1/3. And then if you fill everything in, we get VC of t equals 24 minus 8 e to the negative 3t volts for t is greater than or equal to 0 seconds. Yeah, and that would be your final answer. I still got 15 minutes. I will do a couple more problems, but first let me get some water. Okay, so moving right along. Let's see what looks interesting. Hmm, did I do this one already? Yeah, I did this. Wait, I just did that. Okay, here's another one where the final voltage is 0 again. This one's actually like pretty simple. Actually, this one's like as simple as it can get. Right now, that's microfarads. Make sure you know like micro and pico and kilo. Hopefully, like you're all engineers. You should know these things by now, I would hope. Uh, so this says find expression for current through the 3 kilo ohm resistor. So find I of 3K. And here, again, I would recommend thinking, okay, how does I of 3K relate to the voltage across the capacitor? Because the voltage across the capacitor is what you're actually going to be looking for here. And if we look, right, that 3 kilo ohm is in parallel with the resistor. They share their ends, right? So they're in parallel. And that means that the voltage here is the same as the voltage here. So what that tells me is that I of 3K will simply equal that voltage across the capacitor, which is the same as the voltage across the 3K, divided by 3K. And that would be what we're looking for. So again, we're just finding VC of t. So for t is less than 0, that 12-volt source is in the circuit. So we got plus minus 12, and that goes to the 6K and the capacitor and the other thing. And this is the exact same thing we had right here, right? It's the same circuit. It's just this resistor has been moved up a bit. 6K, 100 micro, 3K, 12. And so we want to find the voltage between here and here. Again, we pretend this isn't here, and we just find the voltage at like this point, right? We always assume that like the minus side of the voltage source is 0, or you pick a 0, doesn't really matter. But yeah, so the voltage across the capacitor though will be the voltage difference between those 2 points. So the voltage difference between those 2 points, assuming we like call this 0, then just makes everything easy, you know. The VC of 0 is going to be that input voltage times 3 over 3 plus 6, which is 1/3 of 12, which is 4 volts. Wow. And then moving right along, t is greater than or equal to 0. This switch moves to the down position, right? And then this part doesn't matter anymore. So we have the same circuit, just, with no voltage source. So we got that 6 kilo ohm a capacitor, which is now charged, right? 3K, 6K, 100 microfarads. And this has some charge on it at the start, 4 volts. However, pretty clearly, it'll go down to 0 because it'll discharge into the capacitors and everything will go away. Which means that if you remember, there are like two equations. We can use this other equation, which is just this equation with VC of infinity equaling 0. So really, again, you only need to remember that. You only need to remember this equation. This is the one. This is just a special case. So where was I? Here. So what we need to find though still is the tau equals RC. If you look at this from the perspective of the capacitor, the two resistors are in parallel. So this is T equals 100 microfarads times that 6K in parallel with the 3K. I don't know if you've seen this notation before, but it's a very nice way to write that things are in parallel with each other. So this is 100 micro times 6 times 3 over 6 plus 3K, which is 100 micro times 24 over, no, 18 over 9 is 2. And this will end up with 200 microseconds, which is the same as 1/5 of a second. Because remember, micro is 10 to the negative 6. Yeah. And so this is a second. And then we plug that into our equation for VC of t. We get, I'll just like write, I mean, you can, yeah. So this part's kind of optional, but you can say that VC of infinity equals 0. Then if you plug that into our equation here, right, we get, keep writing a plus there instead of a minus. Forgive me. So if this is 0 and this is 0, then we just get VC of 0 times e to the negative t over tau. And then this would become, okay, we got 4 volts times e to the negative t over 1/5, which is 4 e to the negative 5t volts for time is greater than or equal to 0. And then we want to find the current through that 3 kilo ohm resistor, which we said earlier is simply VC over T divided by 3K. Because, we have a voltage here, which is just the voltage of the capacitor, and it's going to go down like this because since we've defined basically the capacitor acts as a voltage source here. So we can like just say that this is 0 and then this is the voltage across the capacitor. So this would be like, it's the differences are what matter. Anyway, yeah, it's just VC over T over 3K. So we get 4e to the minus 5t over 3000 or 3K. If you left it as 3K, like if I was grading a quiz and I saw this, I'd be happy with that as a final answer, assuming you wrote amps T is greater than or equal to 0. So like this could be a final answer. If you want to actually divide it out, which you probably should, I guess, it would be 0.0013 repeating, where just the 3 is repeating, e to the negative 5t amps, which if you want to be really cool, you can write as 1.3 e to the negative 5t milliamps for t is greater than or equal to 0. And yeah, so cool. Um, I got a couple more. I still got 8 minutes. Why VC infinity is 0? VC of infinity is 0, because there's no voltage source. If you just have a capacitor that's charged up and you put a resistor across it, then like it'll put all the power into the resistor and the resistor will dissipate it all. If you're in lab and you charge up a capacitor and then you touch the two ends to each other, then there will be a spark and then the capacitor will be fully discharged because it discharges it all through the wire. Um, What if there's a current source? I did a current source question already, right? It's just you still treat it like the exact same. You just do the circuit before and the circuit after, and you leave the current source as if it's a current source. For voltage division, how do you know which resistor is in the numerator? It's whatever resistor is like whichever one you care about, I guess. In this case, right? Which yeah, just did this question. Like if you think of the circuit as um for this top half, right? Oh, you can redraw this as like right? This is 3K, this is 6K, and this is 12. If we're interested in the voltage across the 3 kilo ohm resistor, then the 3 kilo ohm resistor is in the numerator because we're looking at like what proportion of the voltage does this resistor get? So it's that one. Yeah. And that will since we usually define this as ground, that would also be the voltage here. Okay. Another question. Okay. Yeah, I'll just do this, I guess. Um, yeah. Okay. So we got is, is this the exact same as the question I did before? Shit. Wait. Oh, okay. I guess he used this question a couple years in a row. Huh. Never mind, not doing that question. Um, have I done all of them? Might have done all the practice problems I brought with me here. I mean, I just did this one. Um, I did this one, and I did that one, and then I just did, yeah, I did that one, and I did that one. Okay. Yeah, I'm kind of out of practice problems. Does anyone have any particular questions? What would the second question be focused on? I'm guessing you'll have one question where the you'll have one question where the voltage across the capacitor as time goes to infinity is zero, and you'll have one question where it's not zero. I doubt there will be anything about power. Um, yeah. I mean, I guess I could ask for like the power through a resistor over time, where then you'd need to find like the current and the voltage and then multiply them. But they won't, I don't think that'll be on here. This quiz will just be like find the voltage across the capacitor over time and then maybe use that to find some other part of the circuit. Um, Remember if they ask you if you find VC of t and then they ask you to find I, the current through it, just remember that the current is equal to the capacitance times the derivative of the voltage. That's like you can just use that. So if you get like, I don't know, VC of t equals 10, I don't know. Let's just because this polarity kind of does matter here. If we get VC of t equals like 8e to the negative 5t or something, right? Then the current, if you take the derivative, I really hope all of you know how to take the derivative. It would be like negative 40 e to the negative 5t. And since it's negative 40, right, that would mean that the current is going that way. Crazy. Could they act about inductors? Inductors will be the next quiz. It'll be like the same thing as this quiz, but with inductors instead. But no inductors on this quiz, I believe. For the question with the current source for t is less than or equal to zero, why wasn't that side of the circuit considered? I don't know. I think there is yeah, I think you're right. There is no quiz next week. So there's no quiz next week, so the quiz after break will be inductors, I suppose. For the question with the current source, why wasn't the left half of the circuit considered? Um, because for t is less than 0, right? It was like that. The switch was like that. So this part of the circuit, like the left half of the circuit, I guess there was current flowing in a loop here, but that doesn't affect the that would just like charge this up to 4 times 24, which is like 96 volts. But that doesn't matter because it's not connected. It's like remember you just got to consider where you got an actual loop. You know, this is the part that matters. And then you consider the second half once the switch moves and don't consider this. Yeah. Any other questions? In the example you just did with C equals dVdt, oh, C would be like, um, good catch. I completely ignored that. Um, let's say this is like, 10 microfarads. That's a common, or no, that's actually kind of huge. Uh, I've been, for my classes, I've been doing a lot of stuff with capacitors and stuff. I don't know, let's say this is 100 nanofarads. Then the C, my bad, this would be 100 n times 8 or times the negative 5 times 8 e to the negative 5t, which would be oh, make sure you write units. Don't be like me. So you'd get 100 n times negative 40, and that would be like negative 4 e to the or I'll yeah, it'd be negative 4,000 e to the negative 5t nanoamps, which is the same as negative 4 e to the negative 5t microamps. So you just the C is just whatever value is written on your capacitor. Yeah. I just completely forgot to do that for this question or for this example. But yeah, cool. I think we're done. Good luck on your quiz tomorrow. Um, yeah, goodbye.